Hello everybody, and welcome back to this video where I will be talking about problems that go over wavelength, frequency, and the photoelectric effect. Let's get right into it. Alright, so here's our first question. Violet light is 7.1 times 10 to the 14 hertz. What is the wavelength in nanometers of violet light? So I find that the best way to get better at chemistry is to do problems by yourself and then look at a solution problem. So what I recommend that you do is take a few seconds to work through this problem on your own. So pause the video and then come back and we can work through it together. Alright, so now that you've had some time to work on this problem, let's go through it together. So essentially what this question is asking us to do is basically just to convert from frequency into wavelength. And that's pretty simple if you know these two things. So the first thing is that the speed of light is equal to the wavelength times the frequency of that light. And also you need to know what the speed of light is, which is 3.0 times 10 to the 8 meters per second. Actually, let me write it like this. Meters per second. Great. So now we should just plug in whatever we know into this equation right here. So we do know what the speed of light is because I just wrote it down. And so that is 3.0 times 10 to the 8 meters per second. We don't know what the wavelength is, so we're going to leave it like that. But we do know what the frequency is. We know that it is 7.1 times 10 to the 14th hertz, which is also just another way to say per second. So I'm just going to write it like that. So now we need to get our wavelength value all by itself. So what I'm going to do is I'm going to divide by 7.1 times 10 to the 14 hertz on both sides in order to get our wavelength symbol all by itself. So that's what I'm going to do right here. So our wavelength will now be equal to 3.0 times 10 to the 8 meters per second divided by 7.1 times 10 to the 14 hertz or per second. And so when I put that in my calculator, I get 4.23 times 10 to the negative 7 meters. Alright, so now we have a wavelength, but we don't have it in nanometers, which is what the question wants us to do. So if you recall, in a previous video, I said that 1 nanometer is equal to 10 to the negative 9 meters. So essentially what we need to do is, in order to get this to 10 to the negative 9, we need to move this decimal place 2 places forward. And so that's going to give us 423 times 10 to the negative 9 meters, which is 423 nanometers. Alright, so our second question is, a lamp rated at 32 watts and a watt is equal to 1 joule per second emits violet light of wavelength 420 nanometers. How many photons of light can the lamp generate in 2.0 seconds? Okay, so first we need to figure out how much total energy the lamp is putting out over the course of the 2 seconds. So here we know that the lamp is 32 watts, so that's when I'm going to write it down. So 32 watts, which is also equal to 32 joules per second. And then we know that the lamp is turned on for 2 seconds. So that means I'm going to multiply this by 2.0 seconds. The seconds and per seconds cancels out, so I'm going to be left with joules. And so my final answer will be, well, not my final answer, the answer to how long the lamp will be on will be 64 joules. And that's how much energy will be put out by the light over the course of 2 seconds. Alright, So now I need to figure out how much energy one photon of this light source produces. So if you remember, the equation for energy of one photon is equal to Planck's constant times the frequency of that energy. And we have something that's pretty close to the frequency of the light. It's the wavelength of the light. We know that's 420 nanometers. But wavelength is not the exact same as frequency. So if you'll remember from the previous question, we know that the speed of light is equal to the wavelength times the frequency. And so what we can do is we can rearrange this equation by dividing the wavelength on both sides. So we know that the speed of light divided by the wavelength is equal to the frequency of light. And so what I can do is I can essentially substitute all of this in place of this. And so that's what I'm going to do. I'm going to rewrite this equation as energy of the light, of the photon, of a single photon I should say, is equal to Planck's constant times the speed of light over wavelength. So now let's plug in all the units that we know. So just going to rewrite this here. Energy of one photon is equal to Planck's constant, which is 6.62608 times 10 to the negative 34 joules times seconds times, and here I'm going to put the speed of light, which is 3.0 times 10 to the 8 meters per second, divided by the wavelength, which is 420 nanometers, and 420 nanometers is 420 times 10 to the negative 9 meters. So now I'm just going to type everything into my calculator, and I will get 4.733 times 10 to the negative 19. Now what are going to be my units? My units will be, let's see, so the seconds here cancels out with the per seconds right there, and then the meters on top of this divide sign will be canceled out by the denominator. So really all I'm going to be left with is joules. So I'm going to write this as 4.733 times 10 to the negative 19 joules is produced by, remember, one single photon. So if one photon can give off 4.733 times 10 to the negative 19 joules, then how many photons can give off 64 joules? And so this looks an awful lot like a proportion, and that's exactly what I'm going to do. So here I'm just going to write it off to the side right here. I'll do the proportion in blue so that's easier to see. So here we have one photon produces 4.733 times 10 to the negative 19 joules, and that will be equal to x photons over 64 joules. So now I just do cross multiplication, so I multiply that by that, and then I multiply this by this. So what I'm going to be left with is 64 joules times one photon is equal to 4.733 times 10 to the negative 19 times x photons. So I'm going to solve this by doing 64 times the 1, then I divide that by 4.733 times 10 to the negative 19, and I am left with 1.35 times 10 to the 20 photons is needed to produce 64 joules of energy. So our third question is, if 535 million photons are ejected from a light source and hit the surface of an iron block, what is the maximum number of electrons that can be ejected from the iron? Okay, so this question is essentially a photoelectric effect. So let's do a quick summary of what the experiment was. So first I have an iron block right here, or really any type of metal, and on one side I'm going to have a light source. So I'm going to draw this really old school kind of lamp right here, and here are the light rays coming off the lamp, and these light rays contain light particles called photons. And what happens is, one photon, if it has enough energy to overcome the threshold energy of this iron atom, this photon is going to interact with the electrons on the surface level iron atoms, and it's going to interact with only one electron at a time. And what it's going to do is it's going to kick out the electron from the grasp of the nucleus of this iron atom. And so when it kicks out this electron, it's emitted out into space, where it is detected by a detector on the right side. So that's kind of the photoelectric effect in a nutshell. So, like I said, we really expect one photon to be interacting with one electron. So we should be expecting about 535 million photons, or 535 million electrons to be detected. So that gets us A and B out of the way. And so C and D are kind of similar. What we have in C is that we are expecting less than 535 million electrons to be ejected. And so this is definitely a possible scenario. In fact, in most scenarios, you're going to be expecting less than 535 million photons, probably because the photon either doesn't have enough energy to overcome the threshold energy of this iron atom, so it won't be able to kick out the electron, or simply because the detector doesn't detect an electron. But looking at the key words in this problem, we see that we're expected to find out what the maximum number of electrons is. So we can assume that the detector is working perfectly and our photons have enough energy to overcome this threshold energy. So we expect one photon to be interacting with exactly one electron, and so that crosses out option C, and at max we're expecting 535 million electrons. Alright, so these next three questions will be about the photoelectric effect, and they'll all be related to each other. So here's the first part. UV light hits a sodium metal surface, and the velocity of the ejected electron is 6.61 times 10 to the 5th meters per second. What is the kinetic energy of the ejected electron? Alright, so this question is pretty straightforward. It's asking us to basically know what the formula for kinetic energy is. And so that is the kinetic energy of the electron is equal to 1/2 times the mass of the electron times the velocity squared of the electron. And so usually you'll be given this, but we know what the mass of the electron is, which is 9.10983 times 10 to the negative 31 kilograms times the velocity squared, which is 6.61 times 10 to the 5th meters per second squared. And so what we will get is 1.99 times 10 to the negative 19 joules. And so that. So our second part is the work function, or the threshold energy of the sodium metal is 150.6 kilojoules per mole. How much energy is required to remove an electron with no kinetic energy from one sodium atom? Alright, So this last sentence of this question is basically asking us to figure out what the threshold energy of one sodium atom is. However, the question gave us the threshold energy in terms of 1 mole of sodium metal. So first we need to convert this value, 150.6 kilojoules per mole, into 156 kilojoules per atom. So let's go ahead and do that right here. So 150.6 kilojoules per 1 mole. And then some dimensional analysis. So 1 mole is equal to 6.022 times 10 to the 23 atoms. And I'm getting this number because of Avogadro's number. And from there, you know what, let's convert from kilojoules to joules just for fun as well. So in order to get rid of the kilojoules, I need to put kilojoules on bottom. So 1 kilojoule is equal to 1,000 joules. So now let's cancel the units. This is now the fun part of the dimensional analysis. So the units cancel out here, and the kilojoules cancels out here. And so we are left with 150.6 times 1,000 divided by 6.022 times 10 to the 23. And that leaves us with 2.50 times 10 to the negative 19 joules per atom. Perfect. So now we know the threshold energy for 1 atom of sodium. And now we just need to figure out how much energy is needed in a photon to kick out an electron without any kinetic energy. So if you recall, there is an equation that says the energy of the photon minus the energy of the work function, or the threshold energy. So let me write that down. Threshold is equal to the kinetic energy of the electron. But in this case, remember, we don't want any kinetic energy. We want no kinetic energy from our ejected electron. And so no kinetic energy is just a fancy way of saying 0. And so now let's just rearrange this equation to make it easier for us. So the energy of the photon is equal to the threshold energy of the metal. And so the energy of the photon, if we substitute, must be what we figured out, 2.50 times 10 to the negative 19 joules per photon in order to kick out 1 electron in the sodium atom. And so this right here is our final answer for that question. Alright, so our third question is, what is the frequency of the incident light required to eject an electron at 6.61 times 10 to the 5th meters per second from the surface of the sodium metal? Alright, so really quick, I want to clarify what exactly incident light means. Incident light just refers to the photon emitted from our light source. So basically, just to simplify this question, it's asking us, what is the frequency needed for our photon to kick out an electron at this much speed from the surface of our metal? So whenever we're talking about photoelectric effect, we like to use our handy dandy equation, the energy of the photon minus the energy of the work function, or the threshold energy of the metal. I'm trying to use both types of vocabulary here so that you're familiar with it. So we have the energy of the photon minus energy of the work function is equal to the kinetic energy of the emitted electron. And so lucky for us, we do know what the kinetic energy of an electron at this much speed is. It is 1.99 times 10 to the negative 19 joules. So let's write that right here. That is 1.99 times 10 to the negative 19 joules. And now we need to decide what work function we're going to use. Are we going to use this work function that was provided to us right here, or are we going to use this work function that we calculated? So what I'm going to use this work function, because the question is asking us to figure out the energy required to kick out one electron. So since one photon interacts with one atom to kick out one electron, I need to figure out the work function of one atom. And so that's why I'm going to use the 2.50 times 10 to the negative 19 joules per sodium atom. So I'm going to write that right here. 2.50 times 10 to the negative 19 joules. And then finally, fill in the rest of our equation. Energy of the photon is our variable, minus our work function is equal to our energy of our electron. Perfect. So now I need to get the energy of our photon all by itself. So what I'm going to do is I'm going to add this value on both sides. So that leaves us with energy of the photon is equal to 1.99 times 10 to the negative 19 joules plus 2.50 times 10 to the negative 19 joules. Awesome. So now when I add those two values together, I get that the energy of the photon is 4.49 times 10 to the negative 19 joules. Awesome. So now we have the energy of a single photon, but the question is asking us to figure out the frequency of that photon. So, I wonder what other handy equation do we have that allows us to convert from energy of the photon to frequency of the photon? Well, if you couldn't tell by now, it's our good friend, energy is equal to Planck's constant times frequency. So I'm just going to highlight this very important equation right here to the side, and now we're going to fill in all the values that we know for it. So we know that the energy of the photon is 4.49 times 10 to the negative 19 joules. And we know what Planck's constant is. That is 6. Whoa, that is a horrible 6. It is 6.62608 times 10 to the negative 34 joules times seconds times our frequency. And so since we want frequency all by itself, I'm going to divide this value, Planck's constant, on both sides. So what I'm going to be left with is frequency of the photon is equal to 4.49 times 10 to the negative 19 joules divided by 6.62608 times 10 to the negative 34 joules times seconds, and I get 6.78 times 10 to the 14. What are our units? They will be, joules cancels out with joules, so we're left with 1 over seconds, which is just another way of saying hertz. And so our final answer is the frequency of our incident light will be 6.78 times 10 to the 14 hertz. And that wraps up this video. Thanks for watching, and I'll see you in the next one.